Hello everyone. We are going to be starting with section 1.5 on infinite limits. As usual, I do a little recap of things we have done earlier. The things we have talked about is the informal and formal definition of limits. We have learned how to solve limits using numerical, graphical, and analytical approaches. Then we learned about one-sided limits, discontinuous functions, and continuous functions. Here we're going to learn about a special kind of limits called the infinite limits. Before I give you the formal definition, I am going to start with an example. So let's look at this nice little example, which is given by fx equals 3 over x minus 2. So let's look at this graph. So if you draw the graph of this function, clearly, first of all, this is, as you notice, is a rational function. And there is going to be a problem at 2. Because when you put x to be 2, you get 0 in the denominator and a non-zero in the numerator. And if you remember from your algebra days, that means you're having a vertical asymptote at x equals 2. The graphical way of representing is by this dotted vertical line. Now, let's look at things here. And if you draw the graph, you would see the graph actually is like, it's going up and up as the values are going very close to 2 from the right-hand side. And as the values of x increase, the values of the function increase. But in both the sides, they're never ever touching the axis. The first one, as you're going towards x values increasing, this function value will never touch the x-axis. And similarly, when x is approaching 2 from the right-hand side, the function is going to become large and large and large, becomes unbounded, but will never ever cross this vertical line. Now let's look at from the left-hand approach at 2. As x is approaching 2 from the left-hand side, look at the values of the function. It's decreasing without bounds. Okay, so that means that's a very important kind of a function for us. Remember, the limits basically says how does the function behave even though it is not defined at that point. That's the beauty of limits, remember that. Now this was from the graphical point of view. Let's look at from the table point of view. Now 2 is the value here, and you notice as you get closer to 2 from the left, the values are decreasing without bounds. You see, at 1.5 it was -6. Look at the value at 1.999, -3,000. Think of that. Now let's look from the right-hand side. At 2.5, the value is 6. But as you come closer to 2, let's say 2.001, what's the value? 3,000. That's showing numerically that the values are just exploding near 2. But remember, in a vertical asymptote, the graph never crosses the line, the vertical line. These are like your orange cones when you're driving down the road. Okay. So the behavior, let's talk about the observations. So here are some of the observations. What we notice is the limit of the function as x approaches from the left-hand side 2 minus, you see I've written -infinity. I'm going to just draw the graph once over here and try to be consistent with the diagram we have, -2. And let's look at the graphs. As the graph approaches positive 2, guys, it is. As the graph approaches 2 from the left-hand side, notice what's happening. It's dipping down. That means it's decreasing without bounds. But remember, it's never ever going to touch the x-axis, the vertical line given by x equals 2. Now to represent its decrease unboundedly, we write -infinity. The decrease means the negative sign. Infinity means that it is unbounded. Okay. Similarly, when we're looking from the x approaches 2 from the right-hand side, our graph, notice, is just increasing without bounds, but it is never ever going to touch the vertical line x equals 2. That's what we show by infinity. Very important, these symbols, infinity and negative infinity, are not representing real numbers. Very important. They're not representing real numbers, guys. They are symbols which describe the unbounded conditions more concisely. That's important. Remember, negative infinity, infinity are not real numbers. In our sense, it says, oh, the function is just exploding. Either it's exploding very high or it's exploding with a very low numbers. That's the meaning of it. Okay, let's go to the formal definition. Now, a limit in which the function increases or decreases without bounds as x is approaching a real number is called an infinite limit. And this is the nice and a beautiful definition in terms of mathematics. And guys, we will have a look at it and we will say bye-bye because we just want to understand, okay? At the calculus level, we're trying to understand what it is saying. So that's where I will say, and we will now go and do some examples. But if you really are interested in it, please go ahead and read it. My main focus over here is to explain the concept and try to use them in our problems. Okay, let's go ahead and do that. Now, there are two functions here. We would like to find the limit of each function as x approaches 1 from the left and the right. In the first graph A, notice what happens. As the function approaches 1 from the left-hand side, as x approaches 1 from the left-hand side, the function is going up and up, and it's basically exploding. It's increasing without bounds. It's similar the case when the x values are approaching 1 from the right-hand side. The function values are just exploding. So in both the cases, when I look at the limit of the function, as x approaches from the left-hand side, that's the left-hand limit, we see it's positive infinity. That means it is increasing without bounds. And when you look at the right-hand limit, in the same scenario, this function is positive infinity. So when the left-hand limit and the right-hand limit both are increasing without bounds, in that scenario, guys, we simply write limit as x approaches 1 of the function fx equals infinity. That's what we do. Okay? Now, on the other hand, example B, what's happening here? When we look at the left-hand limit, that is the limit of the function fx as x approaches 1 minus. What's happening to the function here? It's increasing without bounds, so that means it's positive infinity. Let's look at right-hand limit. The limit of the function as x approaches from the right-hand side, which is 1 plus, it's negative infinity. Now here, guys, we cannot write as x approaches 1 because the function is when it's coming very close to 1 from both the directions, left and right, the function is going in opposite directions. The x values, I'm saying, if it comes closer to 1 from the left or the right, the function goes in opposite directions, increasing and decreasing without bounds. So in that sense, we have to write left-hand limit and the right-hand limit. Okay, notice these functions, if I look at this function fx and I plug in 1 over here in the original function, we get a non-zero over a 0. And if you remember from your algebra days, that this is basically a vertical asymptote. Similarly, the second graph also has a vertical asymptote at 1. Because plug in 1 over here in the function, you get a negative 1 over 0. And that's where we are going to introduce that definition of vertical asymptotes. So if a function fx, which approaches infinity or minus infinity, as x approaches c from the right or the left, then this line x equal to c is a vertical asymptote of the graph of this function. So what we're now introducing is the calculus definition of a vertical asymptote. What we have learned from a previous was applying the pre-calculus or the algebra definitions. So when you are, I'm going to repeat this again, the limit definition of a vertical asymptote means that if your function, it simply says if the function fx as x approaches c from the right or from the left, the function goes either positive infinity or negative infinity. Okay, in that case, or it can be limit as x approaches c of the function fx goes to positive infinity or negative infinity. That means you are having a vertical asymptote at x equals c. And this is what I have been talking in this note. I'm saying basically if I have a function which is a quotient kind of a scenario, it's a rational function, and the vertical asymptote will always occur at a number when the denominator is 0 but the numerator is not 0. This is something which we have learned in our previous classes, like algebra or pre-calculus. So let me put that in a proper theorem form for you guys. If I have two functions f and g which are continuous on an open interval which contains c, and the value of the function is non-zero of f at c, whereas the value of the function g is 0 at c, then we will be able to find an open interval containing c such that this gx is non-zero for every other x in that interval not equal to c. So it means that the graph of the function hx, which is fx over gx, a little typo, remove that, has a vertical asymptote at x equal to c. For example, we just had done this example here. We have this function at 1 and we had a graph like this. Okay, so the vertical asymptote was given by x equals 1. So let's do examples. Now, find the vertical asymptotes. So clearly, in other words, let's put the denominator to be 0 to get the value where is the happening. So 2x plus 2 is 0. That means 2x is minus 2 or x is minus 1. So clearly, the asymptote is happening at minus 1 because if I plug in f of minus 1, what do I get? A 1 over 0. So what we normally do is to find the vertical asymptotes, we see where the numerator is 0, and that's how we do it. So for this problem, the first problem, the vertical asymptote is given by x equals minus 1. Okay, in the second problem, to do so, what we normally do is, because there are squares, squaring functions here, I'll try to write it in factors to make my life easier and see what values cancel out, what not, and then we make a decision. Now, x squared minus 25, if you remember the difference of squares, is x minus 5 and x plus 5. Okay? And in the denominator, we have x common and x minus 5. Now, according to the denominator, the values where my function will be 0 will be at x equals 0 and x minus 5 to be x equals 5 to be 0. Okay, so now remember here, so first of all, where can the denominator be 0? Okay, that's first we start. The steps are put the denominator to be 0. So that means either x is 0 or x minus 5 is 0. That means x equals 5. Now, there are two values which we get, x to be 0 and x to be 5. But remember, if it has to be a vertical asymptote, what does that mean? You plug in these values in the original function. So you look at f of 0. What's f of 0? It is minus 25 over 0. Yes, that means this is a vertical asymptote. So the vertical asymptote definitely is happening at x equals 0. Now let's check for f of 5. So if I write f of 5 here, plug in this, what do you get? A 0 over 0. What's this? This is an indeterminate form. So that is not telling us that there's going to be a vertical asymptote. No, according to the theorem, it's only x equal to 0 is a vertical asymptote, but not x equals 5. Okay, x equals 5, that means this is an indeterminate form. That's what we know. This is not, guys, remember, a vertical asymptote. Okay, now let's look at the last problem. Fx is x over sine x. Now to do this one, here we look at where the sine function is 0. First we start from that. So you look at the denominators, guys. Sine x is 0 for every multiple of pi's. If you remember this one, this is sine of n pi. So x equals n pi, where n is an integer. Okay. Now remember, when n is 0, what happens? So that means for n equals ... -2, -1, 0, 1, 2, the sine function is going to be 0. Okay. But what happens when you plug in 0? So if I put f of 0, what do I get? A 0 over 0 form. That means it's indeterminate. An indeterminate form does not give us vertical asymptotes, guys, keep in mind. So that means this function, if I put, say, f of 1, what happens? 1 over sine pi, 1 over 0. So if you notice, you plug in any other integer except 0, this function will have a vertical asymptote. So what's the final answer for this question? Fx over x over sine x has a vertical asymptote at x equals n pi, where n is all integer. That's the meaning, it's a representation of all integers except 0. That means all integers except 0. Okay? Now let's look at one more example. It says, determine whether the following functions have a vertical asymptote or a removable discontinuity. Okay, let's look at this function. For a vertical asymptote, what does that mean? It means that the denominator has to be 0 and the numerator has to be non-zero. Okay, so clearly when I plug in -1, x equal to -1, there's a typo, guys, here. So f of -1, what do I get? F of -1 is what? -1 square 6 times -1 minus 7 over 0. So it's a 1 plus 6 minus 7 over 7. Okay, what are we getting? We are getting a 0 by 0 form. When you have a 0 by 0 form, that means it's indeterminate. And also it means that the function has a removable discontinuity. That's the meaning of it, guys. So it has a removable discontinuity at x equals 1. That means there is a hole. And this one is basically a hole. Okay. Let's look at this function. Again, it's a typo here, guys. So if I plug in f of minus 1, what do I get? A minus 1 square plus 1 over 0. I'm getting a 2 over 0. Now that's clear-cut a scenario where the function has a vertical asymptote. So at this point, we say that the function, because it satisfies the theorem we just talked about, has a vertical asymptote, I'm using this acronym, at x equals 1, minus 1. Okay. So, what's the next step, guys? Practice problems for you. Okay. So, here are a bunch of, say, 5 problems. I want you to figure out whether the functions have a vertical asymptote or a removable discontinuity. Thank you.